Okay, this is exam 3 for spring 24. First, I want to know how long does it take the circuit to completely charge this capacitor. It is a charging capacitor. So I'm going to first find the time constant. The time constant is equal to the resistance times the capacitance. That is 4 mega ohms times 3 microfarads. This 10 to the 6 and this 10 to the minus 6 will just go away. So that gives me 12 seconds. It's the time constant, but the total time is 10 times the time constant. So that's equal to 120 seconds. And then for part B, I want to know how long does it take for the capacitor to reach a voltage of 6 volts. Look on your equation sheet and find the voltage for a charging capacitor is equal to 1 V0 times 1 minus e to the minus t over RC. And I want to now solve that for t. So I'm going to go and put in numbers here. So 6 is equal to the total voltage, which is equal to 8. I'm going to go ahead and distribute that 8. 8 minus 8 times e to the minus t divided by 12. And so that's what I'm solving now. So I have negative 2 equals negative 8 e to the minus t over 12. That's 2 over 8 is negative 1/4, so positive 0.25 equals e to the minus t over 12. So then I take the natural log of both sides. That gets rid of that exponential. Now let's see, the natural log of 0.25. Sorry about that, my calculator didn't have that. Let's see, so it's minus 1.38 is equal to negative t over 12. And then to find t, I just multiply that times 12, and I get 16 or 17 seconds. T is equal to 17 seconds. So that's the answer. And that sort of makes sense. At least I know that it's less than the total time. All right, so now number 2. You have a charged particle and there's a 3 Tesla magnetic field as shown, has a speed, and give you the radius. What is the direction that the particle will initially travel? So here I'm going to do the right-hand rule. Let my index finger go in the direction of V. Let my middle finger go in the direction of B. And so that gives me a direction that's either plus Z or out of page. Let's just double check that I had a positive particle here. Okay, it doesn't say, but I will say that it's a positive particle here. Oh yeah, sorry, it does have positive here. And then B, what is the mass to charge ratio of the particle? Well, if you want to look at your cyclotron equation, that is R equals mv over q B. This just as an aside, let's remember where this comes from. So I'm saying that QVB, that is the magnetic force, is my centripetal force. That's equal to mv squared over R. And that's how I get this R is equal to mv over QB. It is important just to remember where that comes from, that our magnetic force is our centripetal force. So R is equal to mv over QB. And I'm looking for the mass to charge ratio, so I'm looking for m divided by q. And so that's going to be m over q is R B divided by V. And it has a mass to charge ratio then of the radius is 2 meters. The magnetic field is 3 Tesla. And then divided by the speed, which is 5 meters per second. So it has a mass charge ratio of 6 to 5, or if you want to call that 1.2, that's fine. Either one is fine. I'll take either. And that is in units of kilograms per coulombs. All right, light ray is in a material with an index fraction equal to 1.2, it enters two other media, 1.1, 1.4. Draw the lines as they travel through the media. Well, here I'm moving from a big index to a low index, so this is going to bend away from the normal. And then as it moves from a small index to a high index, it bends towards the normal. Remember, I think about my wave fronts coming along. Here, it's going to move into the lower index, so it's going to speed up. And so it's going to move in that direction, and our wave fronts will go like that. And here it's going to slow down, so it bends around in that way. Think about our twin track, the tank or the bulldozer, help you really think about our marching band. So that's a, let's see, I will make that bigger. Draw those rays correctly. And then what is the angle of the right ray as it goes? Angle of the light ray as it goes into the third medium. So I'm going to say n1 sine theta 1 equals n3 sine theta 3. N1 is 1.2. Sine of theta 1, that's 30, is equal to N3, that's 1.4. Sine of theta 3. And for that, I get that theta 3 is equal to 25 degrees. All right, that's the answer for B. All right, proton approaches a wire with a current of 3 amps as shown in this figure. It has the velocity and there's the radius. What is the direction of magnitude of the location of the magnetic field at the location of the proton? So we're going to use our other right-hand rule where our thumb goes in the direction of the current and then our fingers wrap around. And that shows us that the magnetic field is into the page on that side and out of the page on that side. So either negative Z or into the page. And now what is the direction of the magnetic force on the proton? So I need to figure out what is the magnetic field? Two steps here. So first, what is the magnetic field? That's going to be mu naught I over 2 pi r. That's going to be 4 pi times 10 to the minus 7 times the current, which is 3, divided by 2 pi times the radius, which is 0.1. So I can get some cancellations here. The pi's cancel. I can get that, and it'll be 2, and well, I can get rid of the 0.1, and that becomes 20. So I get the magnetic field is 60 times 10 to the minus 7. Or that's 6 times 10 to the minus 6 microtesla. So that's the magnetic field. And then I want to know the magnetic force. So the magnetic force is equal to QVB. It's at an angle of 90 degrees, so I'm just not going to write the sine of theta. So this is a proton, so it's 1.6 times 10 to the minus 19. The speed is 4 times 10 to the 5th. And then the magnetic field I've already found is 6 times 10 to the minus 6. All right, so that gives me 38 times 10 to the, what's that, 10 to the minus 14, 10 to the minus 20 newtons. Okay, so that's the end of the free response. Let's look at the multiple choice now. So which of these statements about a household circuit is true? Grounding protects the user from wet conditions. Okay, no. Grounding protects you from faulty devices. GFCI protects you from wet conditions. The GFCI turns off if the incoming current exceeds the outgoing current. Okay, yes, that's correct. As you add more devices to a household circuit, the current increases. Yes, that's correct. The circuit breaker protects the house from lightning strikes. No, not correct. So the answer there is just going to be 2 and 3. Circuit breaker, we have a 1200 watt heater. Okay, no, what this is. So this is going to be 10 amps. What I did there is I said that the current is equal to power divided by voltage. That's 1200 amps divided by 120 volts, and that's equal to 10 amps. Excuse me, 1200 watts divided by 120 volts, and that's equal to 10 amps. So I have 10 amps, I have 4 amps. I just did 480 divided by 120. So if I'm at 14 amps, I'm chugging along just fine. But then I add a 240 watt blender. So that's going to give me to 16 amps. Uh, and so somewhere between 14, where it's functioning just fine, and 16, where it's no longer functioning, is the answer. And so that's going to give me the answer, which is 15. That's the number that's in between. Understand it might be a little confusing. Actually, I'm going to change this to take away option A, so that because it does function at 14 amps, and that could be the maximum, and then I exceed it. So anyway, I'll take away number A. Um, Here, a capacitor charges over 10 time constants. Which of the graphs represents the voltage versus time for that capacitor? We've already had that equation. Remember that V was equal to V naught times 1 minus e to the minus t over RC. So the voltage is going to be an increasing exponential function, so that's going to be C for number 3. What is the voltage of this resistor after 8 seconds? Okay, well this is the same. So I have V is equal to V naught times 1 minus e to the minus t over RC. But I'm not solving for t like I did before. I'm solving for the voltage at a certain time. So that's going to be equal to 16 times 1 minus e to the minus, what's my time? 8 divided by my RC is also 8. And so I'll solve that. 16 minus 16 times e to the minus 1. And I get 10.1, or 10 volts is the right answer, number 4. An electron is traveling with that velocity in a magnetic field that is orthogonal. That means it's 90 degrees. And my magnetic field is B. Notice this is an electron, so Q is equal to 1.6 times 10 to the minus 19 coulombs. It is negative. And I want to know what is the magnitude of the force. The sign here doesn't matter. I'm just wanting the magnitude. F is equal to QVB. That's 1.6 to the minus 19 times V, which is 1 times 10 to the 6, times B, which is 2. That's 3.2 times 10 to the negative 13. D is the right answer, number 5. Which of these statements is true? Magnets have only a north or south pole. Not true. They have both. North poles of a magnet attract? No. Wood is ferromagnetic? No. Uh, so none of these are true. How are natural magnets created? Fossilized dinosaurs are magnetic. Okay, no. Dinosaurs are not even ferromagnetic because there's no metals in them. Molten metal solidifies in the presence of a magnetic field. That sounds right. Let's look at the others, though. Ferromagnetic materials undergo very high pressure. No, that's not correct. Iron mixes with magnetic particles. Okay, no, there's not really any such thing as magnetic particles. All right, so uh, That is correct. Number 7. Three wires carry equal currents. The magnetic force exerted on wire A. Okay, so I need to do two things. I need to first figure out what is the magnetic field generated by these wires. Well, due to this one, it's going to be into the page and out of the page. And then due to this one, into the page and out of the page. So in the middle, I have a wire that has a current in that direction sitting in a magnetic field in that direction. So I want to know now the magnitude of the force or the direction of the force. Let my index finger go in the direction of the current. My index finger or my middle finger points in the direction of the magnetic field, and then my thumb points, not down, I'm sorry, my thumb points up. So number 8 is A. Electron travels, electron, negative particle, make sure we near that. It travels with a velocity in the y direction, the negative y direction, a magnetic field that is in the positive z direction. So that's what my figure looks like. And it experiences a force that is what? Okay. Experiences a force. Well, let my index finger go in the direction of V, magnetic field's out of the page. That gives me a force that is to the left. But then I remember this negative particle, so it has to be D to the right. Positively charged particle in its magnetic field shown was the direction of the force. Okay, well, index finger in this direction, magnetic field is into the page. That's my middle finger. My thumb now points up. So C is the right answer for number 10. Positively charged particle in its magnetic field is shown. What is the force acting on the particle? V, magnetic field is to the right. So it is out of the page in the plus Z direction. B is number 11. All right, what strength magnetic field is needed to hold antiprotons moving at a speed of 5 times 10 to the 7th in a circular path that's 2 meters in radius? They have the same mass as protons, but an opposite negative charge. Okay, so um, is a cyclotron. If you look at my cyclotron equation, if you recall that, it was R equals mv over qb. Um, and I'm looking for B. So let's solve this for B. That's mv over qr. I think that's all I need. Yeah, so m times v. M is well, the same mass as protons, so that's 1.67 times 10 to the minus 27. Look that up. That's on your equation sheet, upper right corner. The V is 5 times 10 to the 7 divided by Q. They have the same mass as protons, but an opposite charge. That means that it's 1.6 times 10 to the minus 19. The sign's not important here. And then times R, which was given, right? Yeah, 2 meters. And if I solve that, I find that it is equal to a 0.261 Tesla. So A is the right answer. Here, a charged particle enters into a mass spectrometer, so another one of these, but here I want you to identify the particle. Uh, so I'm going to identify it based on the mass to charge ratio, which is something that we've done before. Remember that R is equal to mv over qb. So m over q then is equal to rb over v. R is given as 0.16 times b, which is 0.35, divided by v, which is 1.79 million meters per second. I'm going to solve that. I get a mass charge ratio that's equal to 3.13 times 10 to the negative 8. Looking down here, that looks like yeah, tritium, right? So I can just look at this 5 and 1.6. I don't know that 1.6 times 3 is 4.8, so that looks right. But anyway, tritium is the answer. Um, It is useful, by the way, especially if you're pre-med, to be able to just work with numbers quickly like that and not use a calculator. Which of these statements is true about a mass spectrometer? It can determine the ratio of the mass to charge. Yeah, we've seen that several times in this exam. The magnetic field in a mass spectrometer changes only the direction of the particle's trajectory. That's right. It is a centripetal force. And centripetal forces do not change. So make sure I'm spelling that correctly. They don't change the magnitude of the speed, only the direction of the velocity. The magnetic force acts as a centripetal force. Yeah, so all of those are correct. All right, moving on to light. The photoelectric effect demonstrates that light acts as a particle. Remember, Einstein discovered that, or described it rather. Reflection demonstrates that light acts as a particle as well. That was Newton's idea. So C is the right answer. Organize these in range of increasing wavelength. All right, so just looking at these, I know that radio has the biggest wavelength. So I'm just going to go through and look for radio here. So it's not that one or that one or that one or that one. So it has to be C. Let's just double check that. So I have the shortest wavelength, next, next, and then next. Yeah, so C is right. All right, here we got a reflection. Um, this is 30 degrees, that's 50 degrees. Let's just draw it out. So I know that this is 30. That means this is 60. 60 plus 50 equals 110. That means that uh, this angle is going to be 110 or 180 minus 110, which is 70 degrees. That's 70. Uh, That means that this angle is 20. 90 minus 70 equals 20. And so the reflected angle is also going to be 20 degrees. So A is the right answer. All right, light travels from medium 1 to medium 2. And which medium does the light travel fastest? Let's draw our wavefronts. Here it's going to slow down so that this speeds around. So medium 1 travels fastest. This also has a lower n. That's not what I asked, but low n right here, high n right here. But travel faster in medium 1. Light travels through air, strikes the surface of water, so theta 1 is going to be 50 degrees. N 2 is equal to 1.3. What is the angle of the light ray in the water? I like to draw pictures. Help me to think about this. It's traveling in air, so n is equal to 1, and this is equal to 50 degrees. I think I got that right. Light traveling through air, yeah. And then this is n equal 1.3, and then so I can use that to now solve for theta 2. So it's going to be n1 sine theta 1 is equal to n2 sine theta 2. Our 1 sine of 50 equals 1.3 sine of theta 2. If I solve that for theta 2, I find that theta 2 is equal to 36 degrees, which makes sense, right? If I think about it, because I know that this has to bend towards the normal, so it has to be an angle that's less than 50. So I could have gone through and gotten rid of those two answers, and I would have been left with these three. All right, one more. It's total internal reflection. What must be theta 1 be for this to undergo uh, total internal reflection? I just want to double check and make sure that total internal reflection will recur. As I move from a high index to a low index, it will bend away from the normal. So that will give me total internal reflection if the angle is right. I'm looking for that critical angle. So that's 1.5 sine of theta c is equal to 1 sine of 90. And 90, of course, is equal to 1. So it's the inverse sine of 1 divided by 1.5. And that's equal to 42 degrees. So this angle has to be 42 degrees in order to get total internal reflection occurring in this. All right.